Okay, so in the last video we talked about carbon and its 4 valence electrons and why those valence electrons make carbon want to have 4 bonds at all times. What we didn't address, however, is the stereochemistry of the carbon molecule. And what I mean by the word stereochemistry is basically how carbon compounds tend to arrange themselves in 3D space. If we were to take one of the most well-known carbon molecules, which we all know as CO2 or carbon dioxide, this is how this molecule would actually look in 3D space if you could take a microscope and see this molecule on the atomic or molecular scale. Then you would be able to see it arranged in this fashion in 3D space. Why does this compound take this arrangement, however? And I know I've told you that carbon always wants 4 bonds, and this molecule, carbon dioxide, appears to only have 2. But if you look closely, these here are double bonds. Alright? The central atom, in this case carbon, is bonded to each oxygen surrounding it, each peripheral oxygen surrounding it, by 2 chemical bonds. And so this still has 4 bonds attached to it. Right? It still satisfies that rule. But once again, let's explore why this carbon compound tends to take this specific arrangement in 3D space. Why couldn't it have something like these 2 oxygens bonded to the central carbon atom in this fashion, where instead of on the carbon dioxide molecule we have the 2 chemical bonds, the 2 chemical double bonds separated by a discrepancy of 180 degrees. Why couldn't it be something like 90, for example, 90 degrees between the 2 oxygens bonded to the central carbon atom? The way that we choose to account for these differences in chemical arrangements in 3D space is something that we call valence shell electron-pair repulsion theory, or vsper for short. And basically all this theory really says is that depending on the amount of bonds or atoms attached to the central atom, and in this case we're considering carbon the central atom, depending on how many atoms are attached to that central atom, we can predict the geometry of this molecule and the way it chooses to arrange itself in 3D space. And how do we do that? If we were to use this sphere, for example, this circle with a horizontal 360-degree axis coming over here and a vertical 360-degree axis coming over here, forming a sphere, and if we were to input a carbon molecule, or I'm sorry, a carbon dioxide molecule into this, then we would see that these 2 oxygens can move on a 360-degree axis in this direction, up and down, or in this direction, left and right, like that. But because of valence shell electron-pair repulsion theory, we know that these outside oxygens have electrons surrounding them as well. And so if this oxygen, which we'll call oxygen number 1, and this oxygen, which we'll call oxygen number 2, both have electrons present in their outer shells floating around these atoms, then those electrons in those atoms want to repel any other electrons in its general vicinity or area. So if oxygen number 1 has electrons floating around it and oxygen number 2 has electrons floating around it, what we see is these electrons repel each other in a way that makes the atoms arrange themselves as far away as possible from each other. So if this oxygen were to move around in 3D space any higher on a vertical axis of 360 degrees, or any more left or right on a horizontal axis of 360 degrees, what we would have is that oxygen number 2's electrons will start interacting with oxygen number 1's electrons in a repulsive fashion, and they will go back to this linear 180-degree arrangement in 3D space. This is the farthest possible configuration that these 2 oxygen atoms can be in, so that their electrons interfere with each other as little as possible. It's like the theory of magnets. Like repels like. So if we have electrons that are negatively charged, they're going to repel each other because they just don't want to be around each other. Instead of 2 atoms bonded to a central carbon, we could have 3. How would that arrange itself in 3D space? Well, if we were to count this carbon here as the central atom, the blue atom right here, we have to use the same thought process as before. We have to understand that we have two axes, one vertical, one horizontal, of 360-degree spin or free rotation, or whatever you want to call it. And so how would these atoms arrange themselves so that they could be as far from each other as possible? Well, we saw that when two atoms were bonded to the central carbon, the amount of space, either horizontal or vertical, where the atoms could be as far away from each other as possible, was 180 degrees. Because if we divide 360 by 2, we get 180. In this case, we have three atoms, so we could use the same formula. 360 divided by 3 will give us 120. And so therefore the amount of distance between each of these atoms is going to be 120 degrees, and it's going to be on a single plane, just like this linear compound is on a single plane. These atoms aren't going to go any further up on the 360-degree vertical axis, because then they start interfering with each other. And we'll see that when we step up to 4 atoms, that's going to change a little bit. Each individual atom is going to be repulsed so much by its other 3 counterparts that it's going to go further down into this 360-degree vertical axis and further to the left or right on this 360-degree horizontal axis, so that we'll see tetrahedral geometry. And I'll explain exactly what I mean by that. So something very interesting happens, however, when we start to deal with situations in which carbon has 4 individual atoms bonded by single bonds onto a central carbon atom. Basically, what happens is the carbon will start to try to take advantage of the outside plane, the horizontal or vertical 360-degree axis, in a fashion that will give us what we call in geometry and in vsper theory a tetrahedral geometry. And basically that looks something like this. If we get rid of everything here for a second, a tetrahedral arrangement will look something like this. And if we consider this blue right here as the carbon central atom, each of these peripheral outside atoms are going to be separated by a discrepancy of 109.5 degrees. And this is just a natural shape that a carbon with 4 bonds will take, and carbon naturally wants 4 bonds. And so this is one of the most important parts of organic chemistry, is understanding why carbon compounds tend to take the shape that they do. And once we understand that carbon wants this tetrahedral geometry, we can start understanding why these molecules will arrange themselves in 3D space in ways that will either match this 109.5 degree configuration, or will try as much as possible to emulate that. So basically what we get, and I want to show you the shape of it, is a tetrahedron geometry. It imitates or resembles this shape as strongly as possible when we're dealing with carbon compounds with 4 bonds, which is the norm for carbon compounds. And so let me just draw it here so you can, I'm going to reproduce this, and we're going to draw it here. We're going to have something like this, where this carbon kind of goes this way, and then this one's attached to that one, and then we have an attachment here, and then we also have a triangle geometry here forming this tetrahedron shape. So now that we know that carbons take this geometry, we can go a bit further and start talking about conformations and stereoisomers and different arrangement, constitutional isomers of the same chemical compounds. We will understand why carbon chooses to behave in the way that it does when interacting with other atoms such as hydrogen or nitrogen or oxygen or phosphorus or what have you. This is one of the fundamental concepts of organic chemistry, and it must be understood in order to continue learning organic chemistry. So basically, in the bottom, in the description section, I put a website where you can see all the geometries that a molecule should theoretically take if it has 3 atoms bonded to it, or 2 atoms bonded to it, or 2 atoms and 1 electron pair that's freely floating about. basically, if you can understand this concept, then you will have gone a long way into understanding a lot of the more obscure concepts when we start dealing with things called carbocations and planar geometry of the carbon compounds and all that kind of good stuff. I know I haven't explained any of that yet, but it's coming. So hopefully you've enjoyed this video, and please subscribe and rate and comment.